And today I will introduce my PhD topic, utilizing digital twins to enhance energy efficiency in manufacturing systems. For the agenda for today, let's briefly overview what we are going to cover today. We'll start with the introduction, then we discuss our research objectives, then we will detail the energy-oriented digital twins and our proposed framework. And following that, through an example, we will detail our methodology for multidimensional digital twin model extraction. And then we mention the summary and outlook and reflecting what we have learned so far and what we headed in this field. And then finally, I will finish the presentation with my PhD-related publication. Let's start it. So I'll start by highlighting the significant rise in global energy demand, which is expected to be doubled by 2050. This increase poses substantial challenges to energy supply and sustainability, and emphasizes the need for efficient management practices for control emissions and meet global standards. Countries worldwide are responding by enforcing strict regulations aimed at achieving net zero carbon emissions, promoting a shift toward greener operations. This transition, while essential, escalates manufacturing costs and affects competitiveness, underscoring the need for advanced and sustainable technologies. In this context, digital twin stand out as a strategic enabler, and these technologies replicate and simulate the physical system in a virtual environment and provides a practical platform for analyzing and predicting and optimizing the energy usage. Focusing on energy-oriented digital twin, we see digital twin as pivotal in driving energy efficiency. Energy-oriented digital twins, or EODTs, utilize real-time data to understand energy-related behavior of the system and then enhance the system's energy efficiencies. Despite the broad application of digital twins across various manufacturing domains, adoption of digital twins for improving energy efficiency remains limited, and we focus in our research to fill this gap by advancing the functionality and integration of energy-oriented digital twin, and also to enhance the energy efficiency of the system. Our first objective is to develop advanced methodologies to enhance our ability to analyze and optimize energy usage in manufacturing systems. The second objective is to focus on constructing energy-oriented digital twins to simulate the energy dynamic of the physical system and to test innovative scenarios and understand the system. And finally, through this digital twin and understanding of the system, we aim to optimize the system in the way for energy efficiency and other objectives aligned with this. So let's take a look at the framework. Because Manuel is not here, you don't have the full framework for the digital twin. I will try to make it more general. So we have a framework for energy-oriented digital twin in the manufacturing system. Besides that, I will explain you the framework for the normal digital twin that we use and develop in our group. So first of all, at the base of the framework is the physical system, is a smart manufacturing system. In a smart manufacturing system, we have various sensor and IoT devices. These systems continuously generate large data and capture different information. For our case, we capture also the energy-related information, but in general, we generate the data. The normal data that we generate in manufacturing system are event logs. I will show you the event log in the next slides. And then we do the pre-processing, we get the data. So this pre-processing includes the removing the noises, to remove unfinished events, which leads to have processes that are not real in the world. I will explain it again. And then we give this clean data to the next states. In the next state, we will do event labeling. We detect which label is in the middle, what is the events we get and generated from the system. And then we do the knowledge extraction. So we do machine learning techniques for the detect of events and process discovery, such as clustering, classification. And then these methods help us to identify and analyze the patterns and behavior of the data. Here for event labeling, also we might need the knowledge I mean, the expert knowledge included to, for example, we have multiple data, and from this data, we have no label. We don't know which data it belongs to the system. So expert can come and kneel and say that this event is labeled with this item. For example, this label is for B. And with this labeling, we do clustering, we do machine learning, and we detect the further events coming in the system from this machine learning methods and using the expert knowledge. So now we have the complete data and we have the processes using the process mining and data analysis. And then we go to model development. So from the insight, is there any question? From the insight gained from the knowledge, we develop our digital twin model, which here we use PatternNet. So PatternNet is a standard methodology or formalism for the model development using event logs. So event log is a standard form of data generated from the manufacturing system, smart manufacturing system. We use this standard data, and one standard way to generate the model, to develop the model, is PatternNet. So we have the PatternNet here, which we aim to change this PatternNet the way that we can simulate the energy-related behavior also within this PatternNet, which is not possible with the standard one. We'll go further at how we can do this. So we developed a model. We go through the validation. So we have two validation, phase or structural validation. If we have the normal model of the system, so we know how the system behaves before the model development, we can compare the behavior of the system. And then we have output validation. It means that we have, for example, we have different KPIs, output, throughput, energy efficiency, and then we check if the system in the same time duration is behaving the same as the simulation model or digital twin that we have in the same time. So we check them together with the KPIs that we already have defined in the system. And then finally, we have the decision-making support. So once we have the validated model, we can say that we have a digital twin. We use the digital twin for different what-if scenarios to enhance the system finally to support for decision-making in the system. So let's see how we can develop the energy-oriented digital twin simulation models, how we can do this in the system. Let's consider that we have a small manufacturing system that includes a robotic arm using the production assembly process. So in this system, raw material, the process begins with the arrival of raw materials at a regular time intervals. So after a duration of time, we have new materials inside. So in this start, let me show you with the points. Yeah, here. And once the raw material are in the place, if the robotic arm is free, it begins the assembly process. After a certain processing time, that assembly is done, the assembly is completed, and then the product moves to the next stage. And during this period, if there is no raw material between, the robotic arms goes to the idle state. What it means is in two states of assembly process and the idle state of the robotic arm is consuming energy. And how do we want to simulate this model is a question mark for our PhD process, which we are developing now. So in normal digital twin that I have mentioned, we use a standard event logs. And these logs capture process-related information, includes the event type, the ID of the process, and the timestamp. For example, the ID ones, for example, the raw material one, the packet of one, has arrived in the system at time 1, and so on. So defining this event log, you can estimate that from these IDs, events, and timestamp, you can do process mining and you can extract the process flow. So first is a start, then is pre-processing, there is assembly process, and it's done. And then we have the schema of the processes, and then we do the data analysis. It means that, okay, we know that the first event is a start, but how long does it take that we have the start event? So we extract the time duration, the interval distributions. For this, we do data analysis. And then we have the schema or the process flow. We have the time duration of each event, each activity, and then from this, we have the whole system model. But the question is, now we have this model, and our focus was using digital twin to enhance the energy efficiency of the system. So this is how it looks, that After time duration, raw material arrives, and if the robotic arm, it should be a dot here. If a robotic arm is free, then they immediately, this black rectangular shows that this event is immediately. So if we have two tokens, robotic arm and raw material here, then it will be enabled and immediately it goes to the next step. So in this state, for processing or for assembly, it takes time, and after the time duration, the process is ready and robotic arm goes again to the idle state. We have the model of the system in this one, and it can be extracted automatically, as I have mentioned. So we have the digital twin once it has been validated. So it's validated through the KPIs that we mentioned. The KPI of the system maybe is just output and throughput. We have not considered the energy efficiency. If we want to have multidimensional or multi-objective decision support, this system cannot support us because it has not considered the energy efficiency, energy-related behavior of the system. So what is the solution? We have considered that, first of all, we need to expand the event log. So we should have multi-dimensional event log. It's not just for the energy efficiency, it can be included for other dimensions in system, waste generation, CO2 generation, or something like this. So all of the KPIs that we can consider, first of all, we mention, and then we, based on the KPIs, based on the objective of the system, we can define the dimension, the different dimension of the system. So here for energy, we mentioned that we have two states that we consume energy. So for assembly process and for robotic arm. Through the sensors that we have in the system, we generate the data which included the energy consumption of the system. To define it, we have some standards that we should have some stamp we mentioned in the column. So in the future publication, we will explain it. So we have energy stamp that mentions which event is included in the dimension of energy and how much energy has it consumed. For example, for the start event, we don't have any energy consumption. So we mentioned this, that here we don't need to have any sensor, or the energy is not consumed here. But for the second one, for the pre-processing, because the robotic arm was in idle state, from the time that it has been in this state to the time that it goes for pre-processing, we will measure the energy. So for example, it's 132. And then for the next one, for assembly process, for the same ID, when the assembly process is done, again, we capture the energy has been done. So we stamp it step by step by each of the events, same as the time stamp that we used. And from this, we do multi-flow process mining. Through multi-flow process mining, we extract the unidimensional models. So in each of the unidimensional models, we define the behavior of the system in that specific dimension. It means for time dimension, we already have the behavior that I have explained you. But for energy dimension, you can see that in start point, we don't have any energy consumption. So it can be like not contributing transition. So here is like the immediate one that I have mentioned here. So immediately, we don't have any energy consumption. It's not immediately, it's not contributing here. And here we have contributing transition. It means while the idle state is there, or the robotic arm is in the idle state, it consumes energy, and so on for the processing that we consume energy. We integrate these two models. We can consider we have many other models, and then we integrate all of them in one unified multidimensional SPL model. So here, we divide each transition to the total dimensions that we have here is 2 dimensions. So the first one is energy, dimension of time, and then energy consumption dimension. So the first one is the time, as we mentioned for the start, we consume, it takes time to go on with this event or this activity, but for the energy consumption, we are not contributing. So on for the pre-processing, that for time it was immediately, but for energy, it was consuming energy. And finally, for the processing, both of the dimensions are contributing to this activity. So from this model, now we have both, or the dimensions that we want to have finally in the system. We use this model in simulation. So we have developed a library, MDPySPN, that from this MDPySPN, we simulate the already developed model. So this model, that multidimensional SPN model in MDPySPN, and then we go through the validation. Here, the validation is not just output and throughput and input and etc. for the operational processes of the system, but also we include the energy efficiency related KPIs, such as the energy consumption for a whole system, for each asset, non-value adding, value adding processes related to the energy. And once it is validated, then we can mention that this digital twin, this multi-dimensional digital twin, can support us for multi-objective decision making, here also for energy oriented or energy centric decisions. So,
sorry.
Yeah.
Sorry, just to say that 15 minutes have passed, so
Yeah,
you can
it's
take
done.
a few more minutes. Okay, great.
Yeah,
Thank
it's done. So for future work, we will expand our methodology for different industrial sectors, different assets in the system, and we try to refine our model to integrate renewable energy sources to enhance energy efficiency finally, and create tools for automated adoption for dynamic manufacturing conditions. So when the system is changing, immediately we have the same changes in the system for all of the dimensions that we might consider for the system. So here is all of the publications that we already have published in our PhD research. And if you have any question, please feel free to ask me.